Hello, everybody. Today we're going to be doing the 3.6 homework. The 3.6 homework starts on page 162. Page 162, and it has numbers 7 through 12, 20, 21, 25. Ooh, that is not a 5. 25, 27, 30 through 32, and 36 and 38. All right, 36 and 38. So to get started and jump right in, we are on page 162, and let's start with number 7. The instructions for 7 and 8 are list all possible rational solutions for each equation according to the rational roots theorem, then find all of the rational roots. Okay, so start with number 7. Whoa, what just happened? There we go. Start with number 7. The question says 0 is equal to 4x cubed plus 8x squared minus x minus 2. All right, so we can start off by writing out all of the possible rational roots. And as we talked about before, the possible rational roots include the factors of 2 divided by the factors of 4. So we start off with 1 and 2, and then we have 1/2 and 1/4, because 2 divided by 2 is 1, and 2 divided by 4 is 1/2. So the others don't really matter. So from there, what we can do is we can plug this. We can start with our synthetic division. So we can take each of our coefficients and write them down for 8, -1, -2. And I think right here, we essentially already have a suggestion for what we should do, because 4 times 2 is 8 and 1 times 2 is 2. So if we multiply by -2, then we have 4, and -2 is -8. That gives us 0, and then 0. Then we have -1, and -1 times -2 is 2, and we have 0. All right, so now all of our possible rational roots are, we've eliminated 2. So we have, all we have left is 1/2 and 1/4. Let's try 1/2. So we have 4, and then 4 divided by 2 is 2. And then 0 plus 2 is 2. 2 divided by 2 is 1, and we have 0. And then finally, we just have our other option, -1/2. 4 times -1/2 is -2. 2 minus 2 is 0. All right, so our function is 4 times x plus 2 times x plus 1/2 times x minus 1/2. And then from there, we have, we can list our roots, and our roots are the numbers right here, -2, 1/2, and -1/2. So -2 and plus or minus 1/2. All right, on to question 8. We have the function 0, or we have the equation 0 is equal to 9x to the 4th minus 40x squared plus 16. Okay, so let's start off by listing all of our possible rational roots. We have all of the factors of 16 divided by all of the factors of 9. So we have 1, 2, 4, 8, and 16, and then 1/3, 2/3, 4/3, 8/3, and 16/3. And then we have 1/9, 2/9, 4/9, 8/9, and 16/9. All right, let's do our synthetic division. So we have the numbers 9, and then don't forget that this is not x squared, but it's x to the 4th, and this is x squared. So we need to put a 0 in for the x cubed, and then -40, and then a 0 in for the x because it's not included in our equation. So we have 0 and then 16. All right. What do you guys think is a good idea for this one? Well, we know that 16, let's see. We know that 16 is 1/2 of 36. Okay. And we know that 36 is 40 minus 4. So is there something that we can multiply 9 by to turn this right here into 4? And then we'll have 36, and then that'll turn the 36 into, it's not 1/2. It is 4/9 of 16, 9/4 of 16. So I think that suggests what we need to do, and that's going to be, instead of 9/4, we're going to use 2/3 because we have we multiply 2 times. So we want to get 9/4, but 9/4, that's the equivalent of 2/3 multiplied twice, 2/3. All right, so 9 times 2/3 is 6, and then 0 plus 6 is 6. 6 times 2/3 is 4, and then 4 minus 40 is negative 36. Negative 36 times 2/3 is negative 24. 0 minus 24 is negative 24. And then negative 24 times 2/3 is negative 16. All right. And then 16 minus 16 is 0. Now we know that 6 is 2/3 of 9, since we just did that. And then 24 is 2/3 of 36. So why don't we try negative 2/3? Negative 2/3. And then we get 9. And then negative 6. 6 minus 6 is 0. 0 here. Negative 36. And then negative 36 times negative 2/3 is 24. And we get 0. All right. Now the last one, or not necessarily the last one, but the one that we're going to do right now, is this one. We know that 9 is 3 times 3, and 36 is 2 times 2 times 3 times 3. So, and we're multiplying by whatever is in here twice to get to 36. So why don't we multiply by 2? 9 times 2 is 18, plus 0 is 18, times 2 is 36, and we get 0. And then finally, 18 is negative 2 times 18 is 2 times 9, so we want negative 2 times 9. 9 times negative 2 is negative 18, and we get 0. So our function is 0 is equal to 9 times x plus 2, x minus 2, x plus 2/3, x minus 2/3. And that means our zeros are the numbers that we have right here, 2/3, negative 2/3, 2 and 2. So our roots of this function, of this equation, are plus or minus 2 and plus or minus 2/3. All right, number 9, let's do it. A polynomial equation with rational coefficients has the given roots. List 2 or more roots of each equation. All right, so we are given roots of the equation, and all of these roots are either irrational or complex. And we know that if we have one irrational root, we have to have another irrational root. And if we have one complex root, we have to have another complex root. So our first root that we're given is 1 plus the square root of 11. That means we need to have 1 minus the square root of 11, because we have plus or minus the square root of 11. And then the next one is negative 3 plus the square root of 17. So that means we need to have negative 3 minus the square root of 17. All right, we're done with that one. We have number 10. We have 5 plus 12i. So we need 5 minus 12i. These are called the complex conjugates. And there's also irrational conjugates for the irrational numbers. We need to have the irrational number and its conjugate. And then we have -9 minus 7i. And if we have -9 minus 7i, we need -9 plus 7i. Number 11, we have 12 plus 5i. So we need the complex conjugate, which is 12 minus 5i. And we have 6 minus 13, or sorry, 6 minus the square root of 13. So we need the irrational conjugate, 6 plus the square root of 13. Okay, and number 12. We have 5 minus 59. So we need the complex conjugate, 5 plus 59. And we have the irrational number 17 plus the square root of 23. So we need the irrational conjugate, 17 minus the square root of 23. All right, that's everything for page 162, and there's no problems on page 163. So let's flip over to page 164 and start off with question number 20. All right, 20. So for 20 and 21, the instructions are to list all the possible rational solutions for each equation. So the first equation is 0 is equal to x cubed minus 3x squared plus 4x minus 12. So this is similar to using the factor theorem, right? Except instead of having a function, we have an equation. And all of the possible rational solutions are things that multiply to 12 divided by 1, the leading coefficient. So all we need to do for this one is we don't actually have to solve. We just have to write down the possible rational solutions. So we have plus or minus, and then we have 1, because 1 times 12 is 12, and then 2, because 2 times 6 is 12, then 3, because 3 times 4 is 12, that implies 4, then 6, then 12. All right, and we're done with that one. Then we have number 21. In here, our equation is 0 is equal to 2x to the 4th plus 13x cubed minus 47x squared minus 13x plus 45. So all of our possible rational solutions are the things that multiply to 45 divided by the things that multiply to 2, our leading coefficient. So we have we have plus or minus, and then 1. 3 divided by 45 is 15. So we have 3, but 45 is not divisible by 2. We have 5, because 5 times 9 is 45. And then we have 9, because 9 times 5 is 45. And then 15 and 45. And then we have each of these divided by 2. So 1/2, 3 halves, 5 halves, 9 halves, 15 halves, and 45 halves. These are all of the possible rational solutions. There are no other possible rational solutions to this equation. All right, for numbers 25, 27, and 25 and 27, the instructions are: what are all real and complex roots of the following function? Number 25, our equation, they messed that up. Our equation is 0 is equal to x cubed minus 3x minus 52. So all of our possible rational roots are 1 plus or minus 1, 2, 4, 13, 26, and 52. And then from there, we can do our synthetic division. So we have 1, and then 0 for the x squared, and then minus 3x minus 52. In this one, let's see. 52 is 4 times 13. 4 times 13. And 13, right here, is 16 minus 3. So if we have 52 here, 4 times 13, 16 minus 3, right? It's for 13. And then 16 is 4 squared. So we have a 0 here, so we're going to be squaring whatever we put in here. And since this is a 1. So why don't we start off by plugging in 4. So we get 1, 4, 4, 16, 13, 52, 0. All right, so that solves our first root. That's one of our real roots. And then now let's just think about our quadratic function that we have here. We have x squared plus 4x plus 13. And let's think about b squared minus 4ac. Well, b squared is 16. It's going to be 4 squared. And then 4ac is 13 times 4, which is 52. And that's significantly larger than 32. So we know that this is going to have complex roots, okay? So why don't we plug this into the quadratic equation, and we get -4 plus or minus the square root of 16 minus 52 divided by 2. Well, 16 minus 52 is 36. -36, excuse me. And 36 is 6 squared, so we have -4 plus or minus 6i divided by 2. And then we just divide both sides, or we divide the numerator by the denominator, and we get -2 plus or minus 3i. So our roots are 4 and -2 plus or minus 3i. And we're done with that one. Then we have number 27. Number 27 has the equation 0 equals x to the 4th plus 34x squared minus 72. Okay. Let's just take a look at this for a second. 34 is equal to, 36, or 72 divided by 2 is 36, okay? 72 divided by 2 is 36. And then 34 is 36 minus 2. So 34 plus 2 is 36. And then we multiply by 2. But remember, we go from x squared to x to the 0th power, okay? So we're going to have to multiply by the square root of 2 rather than by 2. And then this is 1, right? So we have 2 and then all of that. So why don't we do our synthetic division? We have 1, 0, 34, 0, -72. Okay, why don't we try the square root of 2? 1 times the square root of 2 is the square root of 2. The square root of 2 plus 0 is the square root of 2. And then the square root of 2 times 2, the square root of 2 is 2. 34 plus 2 is 36. 36 times the square root of 2 is 36 times the square root of 2. And then 36 times the square root of 2 plus 0 is 36 times the square root of 2. And then 36 times the square root of 2 times the square root of 2 is 72. And we have 0. All right. And since we have the square root of 2, that means we need to have negative square root of 2. So let's try negative square root of 2. And we get 1 times the negative square root of 2 is the negative square root of 2. 0, then 36. And 36 times the negative square root of 2 is negative 36 times the square root of 2. All right. And then we have 0. And then the next thing we have is x squared plus 36. So we know that we're going to have a complex number, but we know that that complex number is going to be the square root of 36 times I. So that's going to be 6i. We plug in 6i and we get 1, 6i. 6i plus 0 is 6i. And then 6i times 6i is negative 36. Okay. And then finally, because we have 6i, we need to do negative 6i. And we get 1 times negative 6i is negative 6i, and we get 0. Okay, so these are all of our real and complex roots. Our roots are plus or minus the square root of 2, and plus or minus 6i. Okay. I wouldn't usually recommend doing putting square roots into here, because often, as you see in the last question, number 25, we're going to have some number plus or minus the square root of, or plus the complex number, or some number plus or minus the like this one, right? Plus or minus the square root of something. That can make it a little difficult to guess what's going to be inside of it. However, in the case where you have everything, all of your functions are even, okay? So we have an even monomial, and then an even monomial, and then a constant, which is an even monomial. If we have something like this, then our axis of symmetry, we're going to have an axis of symmetry, and that axis of symmetry is going to be at 0. So it's a little bit easier to try this part in there, okay? However, if it's the axis of symmetry, is not equal to the line at x equals 0, then it becomes a little bit harder to do something like this. Anyway, the next question is 30. So for 30 through 32, we're trying to find a polynomial function p of x such that p has the degree and p of x equals 0 has the roots listed. So we're trying to find a polynomial of p equals of degree 2 with the 0, 1 plus 6i. So we're looking for a quadratic function with the 0, 1 plus 6i. And if we have the 0, 1 plus 6i, we need the 0, 1 minus 6i. And then so we can just find our polynomial by saying p of x is equal to x times 1 plus 6i times 1 minus x minus 1 minus 6i. Okay? And then we multiply this together, and we get x squared, and then minus 2x, and then we get negative 1 squared. So we have negative 1 plus 6i times negative 1 minus 6i. That's 1 plus 6i minus 6i, and then minus 36, right? Plus 36. So we get negative 2x plus 37. All right. That's that. And then, so this is our polynomial function. And then we have number 31, which is a polynomial of degree 4. And the zeros are 3 minus the square root of 11 and negative 9i. So we know if we have the 0, 3 minus the square root of 11, we need 3 plus the square root of 11. And then we know we have negative 9i, so we need plus 9i. Okay. And then that means our polynomial is equal to x minus 3 minus the square root of 11, and then times x minus 3 plus the square root of 11, and then x minus 9i times x plus 9i. Okay. And now we just have to do our multiplication, and we get x to the 4th. Let's multiply just one at a time. So we have x squared times, that's going to be minus 6x, because we have the minus 3 for both. Oops. Minus the square root of 11. And then negative 3 plus the square root of 11 times negative 3 minus the square root of 11 is equal to 9 minus 11, which is negative 2. We get negative 2. Okay. And then This is multiplied by x minus 9i is going to be x squared plus 81. That's what this one's going to be. X minus 9i times x plus 9i. And then we can cross multiply again. I get x to the fourth minus 6x cubed minus 2x squared plus 81x squared minus 81 times 6 is 81 times 6 is 486. 486 x, and then 81 times 2 is negative 162. Okay, now we can just do our addition. X to the fourth minus 6x cubed plus 79x squared minus 486x minus 162. And that is our polynomial. And then we just have a couple more problems left. We have number 32. And then also we have 36 and 38. 36 and 38 go by pretty fast. All right. We have number 32. We have a polynomial of degree 3 with the zeros negative 5 and 4 minus 8i. That implies that we need 4 plus 8i because we need the complex conjugate. So our polynomial function is equal to x plus 5 times x minus 4 minus 8i times x minus 4 plus 8i. And then let's start by multiplying together the complex numbers. So that's going to be x plus 5 times x minus 8, x squared minus 8x. And then 4 squared is 16 plus 8 squared is 64. So we have 16 plus 64 is equal to 80. Plus 80. Okay. And then we do our multiplication again, and we get x cubed minus 8x squared plus 80x plus 5x squared plus minus 40x. And then 80 times 5 is 400 plus 400. And we can just simplify to x cubed minus 3x squared plus 40x plus 400. And there's our polynomial. We can multiply it by a constant, but this is the base polynomial that we need. And finally, we have 36. 36 is a question that says a fifth degree polynomial equation with rational coefficients has the roots 3, 8i, and 7 minus the square root of 5, which are also roots of the polynomial equation. Select all that apply. Well, if we have 8i, then we need minus 8i, so we have to fill in b. And then if we have 7 minus the square root of 5, we also need 7 plus the square root of 5, so we fill in e. That's number 36. And then 38, performance task. The table shows the number of possible real and imaginary roots for an nth degree polynomial equation with rational coefficients. So if you read the table, you get that a degree 3 polynomial can have 3 real roots and 0 imaginary roots, or 1 real root and 2 imaginary roots. And then a fifth degree polynomial can have 5 real roots with 0 imaginary roots, 3 real roots with 2 imaginary roots, or 1 real root with 4 imaginary roots. Part A. List all of the possible combinations of real and imaginary roots for a 7th degree polynomial equation. So for a 7th degree polynomial, we can have 7 real roots. It's a lot of real roots. And then we can have 5 real roots with 2 complex roots, because all of our complex roots have to be multiples of, you have to have a multiple of 2 of them. For each complex root, there has to be another one. That is the complex conjugate. And then we can have 3 real roots with 4 complex. And then we can have 1 real root with 6 complex roots. All right. Now on to part B. What do you notice about the number of real roots of a polynomial equation with an odd degree? Well, there's always an odd number of real roots. We can either have 7 real roots or 5 or 3 or 1. And the reason is because our functions are odd. A odd degree polynomial function either looks like this or it looks like this, right? So it has to cross the x-axis at least once, or it can cross the x-axis multiple times. But because it starts in one direction, it starts either in plus or minus infinity, and it goes to minus or plus infinity. It goes in the opposite direction as it put in higher and higher numbers. Because it's odd, we need to cross the x-axis an odd number of times. That is one reason why we call them odd polynomials. All right. I hope everybody learned something today from the stuff that we studied. If you need to go back through and watch the video again to get all of the answers down, I know I went through pretty fast, but I hope you get everything in and have a great day. Thank you.